Welcome, everyone, and thank you for taking the time out of your day to join us for our new product rollout event covering our ultrasonic imaging camera, the Si124. So, FLIR's sales enablement training team, working with our business development team, have put together this product rollout webinar to help focus on the strengths, capabilities, and positioning in the market for this new FLIR product. So if you have any questions or comments during the webinar, please use the question pane that has been superimposed on the right-hand side of your screen. At the conclusion of the webinar, we will hopefully have some time where we can address questions live on the air, but in the event that we do run short on time, any questions that are not answered on this session will, of course, be answered in a follow-up email shortly after the conclusion of this event. So I now invite you to sit back, relax, grab a cup of coffee, because we are about to get this show on the road. So we want to talk a little bit today about our new Si124 ultrasonic acoustic imaging camera. I just want to give you a quick overview of what this might look like, and we're going to go into a little greater detail on the applications for this technology and some of those features and benefits that we can give our customers. But really, we just want to show how quickly we can visualize some of these ultrasonic sources that we see coming from a multitude of different equipment out there in the industrial, manufacturing, electrical types of settings. So with that said, let's first talk a little bit about what's that sound, right? That's the title. And as you look at the chart here, you can see the approximate frequency ranges that correspond to ultrasound, with a rough guide of some of those applications. Let's take a look down at the line across the bottom. You can see acoustic located there in blue. That is what humans can hear, somewhere between 20 hertz and 20 kilohertz. You can see above that is the ultrasound, right? These are things that humans cannot hear, but shortly above the acoustic area is areas that animals can hear, right? We know dogs have a better sense of hearing, dog whistles, things like that, not including the political type. And then if we go even further up the ultrasound line here, you can see that medical and destructive, right? We use ultrasound pulses or waves sometimes to, destroy little things inside the body, maybe, so you don't have to have a surgical thing. So if you go even further up, you can see above 2 megahertz, the diagnostics and NDE section. And this is where we play in. And this is where we actually are listening for things that cannot be heard, but can be discerned by our technology. And just for an example, if you look down below the acoustic area, the red, right, that's the infrasound. This is wavelengths that human ears cannot hear, just like infrared are wavelengths that human eyes cannot see. So when we look at these different technologies, we've talked about sound, and I mentioned that this is just another modality, another technology we can look at with condition monitoring as an entire application source here. And these are some of the things that you might see in these kinds of DIPF curves, and some of these common monitoring tools that we're familiar with from a reliability, from a maintenance standpoint. We have everything from oil analysis to vibration to thermographic inspections. We have ultrasonic power analysis and so many others. So as we kind of look at this curve, when you're looking at equipment from the original design stage all the way through this final stage, some of these different technologies can really be used in conjunction with others throughout this arc. So FLIR Systems is commonly known in the industry to have expertise in thermography, and as we add other technologies, ultrasound gives us a whole nother level to our sixth sense, right? Beyond even infrared with the ultrasonic frequencies that we're going to be able to pick up with this technology. So what is ultrasound? Well, we've already shown that ultrasound is basically high-frequency sound waves or vibrations, right? We also saw that ultrasound, by definition, is beyond the range of human hearing. So we're going to talk a little bit about that and try to understand what kinds of things produce these high-frequency sound waves, like gas leaks, emissions, and other types of failing equipment. As you can see as we move down these bullets, ultrasound is very directional. The ability to localize the source of these ultrasound vibrations really helps us center in on pinpoint the intensity of that sound and exactly where it's emanating from. Ultrasound is just another tool that can be used in condition monitoring reliability environments because it provides early warning of a potential failure, just like thermal, gas leak detection, and other technologies that we provide. So when we look at all the different technologies, we begin to see that each of these FLIR solutions is just one part of our comprehensive asset monitoring and management system for critical equipment. So why would we do ultrasound imaging as opposed to just standard ultrasound? And the key here is that we're using multiple microphones in our Si124 in order to triangulate the source of that sound. We We create a sound map and then superimpose that map on a visual image that allows us to easily describe the intensity of the sound source and where it is in the piece of equipment. Ultrasound imaging has only been practical recently due to the combination of really powerful yet low cost computing power and simultaneously the relatively recent advent of small, low powered digital microphones. So the net result there is we are performing ultrasound inspections in the way that is able to reduce the time that it takes to do an ultrasound inspection by approximately 90%. Okay, so what's the best frequency range? Well, this graph shows a blue line which represents the power of the noise generated by a compressed air leak as a function of frequency. You can see the peak of this curve is from around 15 kilohertz to about 30 kilohertz, and this is laid against the noise generated by background machinery in a noisy manufacturing plant. So this is actually recorded in a manufacturing plant where the noise peaks below 10 kilohertz and steadily decreases with increasing frequency. To detect and identify defects with ultrasound, we need a combination of the frequency range with the strongest signal. But it is also strongly directional and a signal that has a signature that can be discerned from the background noise. To put it another way, when the blue line is above the orange line is the sound frequency that's easiest to find leaks. So the 20 to 30 kilohertz frequency range will allow you to detect the smallest leaks possible at a given distance. So something that's important to know about sound waves is that the higher the frequency of a sound, the less distance it will travel. Right? It's simple science. We found the distances needed to image partial discharge, for example, in outdoor electrical equipment. The best performance is between 10 and 30 kilohertz. Here we're showing a typical inspection of outdoor high voltage equipment where you really don't want to get too close to the equipment for some pretty obvious reasons. Something to keep in mind is that when your system goes to higher frequencies, it not only provides no benefit to you, it actually results in reduced performance because the dynamic range of the microphone digital signal is spread across a broader range of frequencies. So why so many microphones? Well, these systems separate the noise we want to hear from the noise we don't want to hear through advanced signal filtering, beamforming algorithms, and the geometrical design of the camera. So why build a system with so many microphones? Surely having fewer microphones would be less expensive, and you could provide the technology at a lower price. And while that may be true, you can see the benefit of having many microphones on this slide. At the top, with only one microphone, we're unable to discern the noise generated by the ultrasonic source. On the second line, with 32 microphones, we can start to discern the source of the sound at 16.5 kilohertz. And on the bottom graph, with 120 microphones, we pick up sound peaks at 16.5 to 18.5 kilohertz. So having these multiple peaks means we can better locate and characterize the signal. That's a complicated way of saying more microphones mean better detection and longer distance range. Another reason why more microphones is better is because it's better at locating the exact source of the issue in question. Just like with a common digital camera or thermal camera, more microphones is like more pixels. The more you have, the better detail you can generally achieve. Here, we're just illustrating the concept by giving an artist rendering of the microphones as if they were a bunch of pixels, easily able to locate the source of the sound. So to conclude, ultrasound technology is an effective method to detect electrical partial discharge, leaks, and other equipment issues as part of a complete asset management system. Ultrasonic imaging improves on the non-imaging technology and makes it easier and typically around 10 times faster. The optimum frequency range for the majority of issues is between 10 and 30 kilohertz to be able to detect the smallest issues at the longest distance. And finally, more microphones mean better detection performance and better pinpointing of defect location. So let's talk a little bit about the applications themselves, right? There are many applications for ultrasound technology. Electrical partial discharge, compressed air leaks, vacuum leaks, refrigerant gas leaks, and many more. But the ones that tend to have the biggest return on investment for most users are the three that we've highlighted at the top here. Electrical partial discharge, compressed air system leak detection, and vacuum leak detection. So let's talk a little bit about the compressed air leaks. When the Si124 is hearing compressed air leak, what it's actually hearing is the noise that's being generated from the transition of laminar flow of the air inside the compressed air to a vortex created when the air escapes from that pressurized container. So these air modules bounce together, creating that high frequency ultrasound noise. So it's important to remember that the leak may not produce enough noise to be distinguishable from the background noise itself. For example, very small methane leaks, like those required to be detected in the upstream oil and gas industry, may not be detected with this method. A vacuum leak produces turbulence on the inside of the component, which means less noise is going to be transferred to the actual camera trying to monitor the condition. And so, depending on the size of the vacuum leak, it may not be detectable. So, today we're going to focus on compressed air leaks. We know these are detectable in most cases. So, where do we look for air leaks? Well, these systems leak a lot because they're complex and they have many, many connections. So, here's a diagram showing the typical components in a compressed air system. Every one of these red boxes presents a potential leak source, right? Couplings, tubings, fittings, joints, traps, valves, you name it. So, why do we do this? The U.S. Department of Energy estimates up to 30% of a manufacturing facility's electricity is consumed for compressed air. That is a lot of electricity. So, on average, a third of compressed air is wasted due to leaks, misuse, pressure drops, and overpressurization. And finally, based on a typical manufacturing facility's running of a 200 horsepower compressor for 6,800 hours per year and 11 kilowatt hours, that gets us an annual potential savings of over $38,000 in that facility alone, which is a lot of money, right? It quickly pays back the cost of the system. So now let's talk a little bit more about partial discharge applications. So far, we've focused in here on compressed air leaks, but another big application we run into is partial discharge. So it's important to understand what partial discharge means. And there's really three actual ways that we classify partial discharge. Uh, and the first one is corona, which is an ionization of fluid or air surrounding a conductor. We'll also talk about tracking, or surface tracking over contaminated insulation. And of course, arcing, right? Electrical breakdown of gas producing a plasma discharge. So these are the three common classifications of partial discharge applications that are achievable using our Si124. So let's take a look at corona, right? Corona is an electrical discharge brought on by the ionization of a fluid, such as air surrounding a conductor that is electrically charged. Now, spontaneous discharge naturally occurs. So when you're walking around some of these high voltage systems, which could be a substation, it could be a generating plant where we're taking that power and converting it, you'll generally hear it in the atmosphere, right? Some say it's got to be over 1,000 volts to hear this audibly, but that's not always 100% true, right? We've seen some of these audible buzzing sounds, continuous buzzing sounds, right? Can actually occur in systems as low as 500 volts. So why is corona bad? Well, in these high voltage systems, especially in the transmission side, you're talking about power loss. This audible noise I just talked to you about, right? You can hear this buzzing. Well, some of the towers might be located in residential areas where people can say, hey, I can hear this constant buzzing in the background. And just as the image of the previous slide showed, corona can sometimes produce a visible purple glow. Corona can potentially do damage to the insulation, creating a failure point for this entire electrical system. So that's one of the biggest reasons why the Si124 is valuable to customers, to be able to detect some of this corona early on in its infancy. One of the other methods of classifications, or partial discharge, that we've just mentioned was tracking. And when you look at tracking, it's a breakdown of a small area in the insulation. Tracking is different than corona, and then it starts almost silently, right? You don't really hear it, like the big buzzing sound we talked about for corona, until you actually hit a flashover or marking event, which may create some intermittent buzzing or popping. But this is random, right? It's not a constant buzzing like corona produces. So this kind of gives you an overall graphic, I think. One of our folks in the ITC team was able to find this video that gives you a good visual of how tracking happens, right? It almost looks like a lightning bolt on this piece of wood. So generally, tracking occurs due to a breakdown in the insulation system or contamination of some of these components, which creates this sort of tree-like growth of damage shown in this visual example. So the third classification of partial discharge, as I mentioned already, is arcing. And as we look at the image in the background, you can see that arcing is an electrical breakdown of gas. But arcing is differentiated by a series of prolonged discharges that almost look like lightning bolts in the atmosphere. And even though we're primarily talking about high voltage systems today, arcing is actually characterized by intermittent low voltage discharges that need to be identified when they occur. So when we look at the electric power utility industry, I just gave a few examples here. Number one, we talked about corona detection in these substations, transmission lines, electrical switchgear, transformers, cables, etc. So looking at a lot of these types of failures when you're observing your application with the SI124, they can become quite obvious. You might see the cables, you might actually see the failures on surfaces, connectors, and things like that. And another application you might find is applications with high voltage motors and generators, right? You can actually look at stator windings and start to detect some early onset of partial discharge. So in the utility industry, you have a lot of great applications for the SI124. Just to reiterate, where do we look for partial discharge or failures? Well, transformers, insulators, pipes, lightning arresters, cables, bushings, circuit breakers, etc. There are a lot of different places and points of failure. Anytime there's a connection, anytime there's insulation, ultrasound just gives you that whole other sense of the ability to detect this early on. But ultrasound technology can also be used in the industrial manufacturing space as well. When we're looking at using ultrasound, there are multiple points of failure you can look at. For example, inspection of electrical panels themselves. When it comes to safety, prior to opening up some of these high voltage panels, we can listen for anything amiss via ultrasound. We want to make sure we keep people safe. In addition to that, we can look at bus ducts. That's another area that we might be able to, take our system and point it upwards. So any switch gear, electrical panels, these overhead bus ducts, you can see the arrows pointing them out in the bottom picture on the right. These all can be inspected with our SI124, from joints to enclosures, terminal boxes. There's just an abundance of areas where potential failures might occur in these electrical systems. So when we talk about the different applications where ultrasound imaging can be used, we need to understand how the addition of this technology can improve the ROI, or return on investment, when monitoring for partial discharge. We can see some of the bullets here: a 5 to 10% cost savings in operation and maintenance times, 10-time reduction in inspection times, 20-30% reduction in maintenance costs, and the big one, right, a 70 to 75% decrease in breakdown, which ultimately, at the end of the day, in a lot of these different plants, whether it's an electrical or utility company or manufacturing facility, what we're here to basically reduce is downtime, right? So a 30 to 45% reduction in downtime is definitely achievable when you look at adding ultrasound technologies to your preventive toolkit in your reliability and maintenance programs. So let's talk a little bit about the camera itself, some of the specific features built right in. One of the things we really wanted to make sure that we did when we brought this product to market is we wanted to make sure that it fit with the aspects of our infrared cameras. We wanted to make sure it was rugged. We wanted to make sure it had the best performance. We wanted to make sure it was easy to use. And we also wanted to make sure that it worked as a tool for our customers. So we created a system where we deliberately set out to make sure that the system met all of these things that are part of the DNA of FLIR thermography cameras. So number one was 124 microphones. This is the best performing system in the industry. And it's the best performing because it has the most microphones. We can actually see compressed air leak with leak rates as low as 0.016 liters per minute. That's a very, very small leak. It's not as small as they can get, of course, but it's still an extremely small air leak, and that's from 30 centimeters away in a quiet condition. For noisy environments, we do need the leaks to be a little bit larger than that. We also wanted to make sure that this system was safe to use, so we made it lightweight and portable, only 2.2 pounds, and we designed it to be operated with one hand and one hand only, right? That's so our other hand can be used to hold onto a railing, a pole, something like that, wherever it is you're in your environment. By just using one hand, it's just going to make it a safer environment for you to operate in. And we also wanted to make sure that, people can use our products at a safe distance from the objects that they are trying to monitor, again, for obvious safety reasons. And that's why this system works from up to 100 meters away to be able to see these partial discharge issues. With our long 8-hour battery operating time, it's able to put in a full workday. And then finally, back to the simplicity issue, we want to make sure that all of our products are really simple and powerful to use. So there's a built-in processing power to get instant analysis. There's future smart analysis via the web reporting tool. The display is nice and bright and large, so you can easily see the results clearly. So here I just wanted to show a few additional specs. I would highly encourage anyone who is interested in looking at the full specs of the SI124 to go to our customer support website, flir.custhelp.com, for more information. So now let's talk a little bit about our cloud-based analytics. And what we're really trying to exploit here is our AI models. So when we talk about this cloud-based analysis, you have the ability to take the information, the data from the system itself, and upload this information via Wi-Fi. So even if you're out in the field, you don't have access to Wi-Fi, you can store all of the images right on the system itself. When you get back to your office, or perhaps you're in your hotel room, or maybe even connected through your mobile hotspot, you could upload this information into our cloud. And what our analytics do is quickly calculate, estimate, basically, the yearly energy expenses due to compressed or vacuum leaks. You could determine if service or replacement is necessary by classifying that partial discharge. So not only do we provide the AI model for vacuum leaks, we also have AI models for partial discharge. And once you have all this information accessible to you in our cloud, it's an easy tool to create reports from. You can see this information, quickly saves information in a PDF file so that you can now export it and send that off to the appropriate teams for possible repair or possible change out of that equipment. Our cloud-based analytics is a really powerful tool, and we keep adding to it so it'll get smarter and smarter as time goes on. So here's just an example of output from a system itself. You can see the data that we capture and display. You see a very large image, and as indicated by the color scale, the intensity of the sound that we were able to detect. And you can even see where the system itself can calculate the size of the leak and provide savings estimates that you can add to the display. It's all editable, at your leisure in terms of annual savings from the fixing the problem itself. You can see the timestamps, date stamps, where it was synchronized with our AI model. So again, these are just some of the data points you're going to be able to pull into our cloud-based analytics system. And from here, you can quickly build out reports for further determination and follow-up. So we wanted to show you just a couple of example images as we close this out here. We're not going to spend too much time, but pictures can help you visualize some of the things that we've been talking about. So you can see here, this is a refrigeration system leak, and we can see the ice forming all over the system, right? It's pretty straightforward in this case. But at this point, we can actually see this with our eyes, right? Long after partial discharge detection would have identified this leak, maybe. So you wanted to be able to show you an image of something that clearly was not using it, and this is the result sometimes of these refrigeration system leaks that we can sometimes run into. So here we have an image of a pump. This basically just shows there are other types of leaks that can be detected beyond partial discharge or compressed air, etc. Right? Looks like there's a sound coming from that particular spot, and that's why the different colors allows us to be able to determine, where that sound is coming from. Now here we have a solenoid valve leaking. Right? It's a very common occurrence you might see in the field. You can see we have identified exactly where it is occurring based on that ultrasound technology that we're using. Here's an example of surface discharge on insulators, electrical power cables, something that we definitely want to be able to identify as early as possible before it can do much damage to our system. So let's take a look at what you get in the box. Of course, we have the camera with the long-lived battery, up to 8 hours of operational time. We have a battery charger. There's a pouch to hang on your belt, right? It supports the weight of the battery to make the unit that you hold in your hand even lighter, all right? Because it's a one-handed operated device, as we talked about. And some USB sticks in case you don't want to take advantage of the automatic Wi-Fi data transfer. You can then transfer the data manually using these USB sticks. And of course, like our thermography cameras, the system comes with a 2-year warranty. So you might ask yourself, how do I use the system effectively? How can I learn to use it effectively? Well, through our infrared training center, we've already built out an introduction to the Si124 and a little bit about basic ultrasound theory. So you can find a lot of this information available for your review at any time that you need it.